In this video, I introduce inverse reinforcement learning. When we use reinforcement learning to find the optimal policy for Markov decision process, we always assume real-world function is known. However, using different real-world functions R, the reinforcement learning model will generate different results. It turns out that design of a real-world function R will be a big challenge in reinforcement learning. Inverse reinforcement learning is a method to find the real-world function for the optimal policy. For example, if policy pi, we use the optimal action A1, that means agent at a state S. If A1 under the policy pi is an optimal action, that means this Q value for the optimal action A1 is greater than any Q value for the action A. According to the definition of the optimal action, this is the Q value for the optimal action A1, and this for Q value for the action A. According to this relation, we can get this condition. So once we have this condition, we can use it to find the real-world function R. However, we have many different ways to find the different R from this condition. However, we find this R because we need to use this R to make the policy optimal. So one natural way to choose R is make the the policy optimal. Say this optimal policy is A1, and we need to maximize the sum of this difference. The first term is the Q value for the optimal action A1. Second term means we need to search action in the action space except the optimal action A1 and make this Q value maximum. Want to make the maximize this sum of this difference. This state is a state in a state space. And once we have this condition and this maximum problem, we can combine them to get the optimization with the constraint problem. So we have this optimization with the constraint problem here. This part, this is just we for example, agent here, we need this optimal policy. We need a search, and the policy, we need a search for the action A, make this term minimum. Once we have this minimum term, then we need to find the maximum of this term, sum of this term. And with this constraint, this is the condition above, and each real world should be smaller as the maximum. So we have this idea, how can we find the real world function for the optimal policy? And then let's see a simple example. If the real world R is linear, then we can approximate R in this formulation. That means this basis function is fixed and known, and alpha as a coefficient. And we need to solve the problem, solve the equation to find this coefficients. From these equations and the basis function, we can calculate the real world R. However, we cannot solve using, for example, the linear programming to solve this R, alone, because this R should be connected to the optimal policy. For this reason, we use the same coefficients alpha to express the state value function and the policy pi. And then we have we already combine the R, the real world R, and the state value function V. So for the optimal policy A1, and then we according to the definition of the optimal policy, we have this relation, because here we have an agent here at the state S. For the optimal action A1, we calculate the expectation of this state value function over all the next state from below this point, because this optimal action is larger than any state. From this point, we calculate the expectation of the state value function over all the next states. And then we use this relation in the optimization with the constraint above. We get this optimization problem with the constraint on the coefficients alpha. The inner part, which is like we mentioned before, we try to find the action in the action space except the optimal policy A1. And then we find that we need minimize this difference. The first term corresponding to the optimal action, and the second term corresponding to the action A. Once we find the A makes this difference minimum, then we solve this, make this sum of this difference maximum to find the coefficients alpha. Once we find this alpha, and then from definition of the real world function R, we can get the real world R. Once we have this R value, and then we can use reinforcement learning to find the optimal policy pi. For more details, please check with this reference. Thank you. Bye.